I.O.W.N, Innovative Optical and Wireless Network, is an ambitious project aimed at radically transforming the future of communication and computing infrastructure. It achieves this by leveraging cutting-edge technologies like photonic networking, silicon photonics, and disaggregated computing to significantly enhance speed, latency, energy efficiency, and scalability in data transmission and processing. Let's break it down step by step and explain how I.O.W.N works in a detailed but understandable way, including its core components, materials, and technologies. 1. Photonic networking. Harnessing light for data transmission. At the core of I.O.W.N's architecture is the All-Photonics network, I.O.W.N. Unlike today's communication networks that primarily rely on electrical signals carried through fiber optics, I.O.W.N's vision is to use photons, particles of light, to transmit data at nearly the speed of light. This would reduce latency, the delay in transmitting data, to the absolute minimum possible, less than 1 millisecond in many cases. Key components. 1. Photonic fibers. Instead of relying on traditional electrical signals, I.O.W.N uses optical fibers to carry data in the form of light. 1. These fibers are made from glass or plastic, which can guide light over long distances with very little loss of signal quality. 2. Silicon photonics. A major innovation here is silicon photonics, where light is manipulated using microchips made from silicon. 2. Silicon photonics integrates optical components like lasers, modulators, and detectors onto the same silicon chip, allowing for faster and more energy-efficient data processing. Why light is important? 1. Speed. Photons travel at the speed of light, about 300,000 kilometers per second in a vacuum, allowing for near-instantaneous transmission of data. 2. Low latency. By eliminating the need for converting signals from light to electricity and back, data can travel more quickly between points. 3. Energy efficiency. Photonic networks use less energy because light travels through the fibers with very little resistance, unlike electricity which generates heat and loses energy over distance. 2. Data-centric infrastructure, DCI. Scalable and disaggregated computing. Another crucial component of I.O.W.N is its data-centric infrastructure, DCI. This is a highly flexible computing model where hardware resources, like CPUs, memory, and storage, are not tied to a single device. Instead, these resources are pooled and shared dynamically across networks, creating what are called logical service nodes, LSNs. How it works. 1. Disaggregated computing. DCI breaks traditional computers into separate components, e.g., CPU, GPU, memory, and pools them in a network. 1. When an application or user needs computing power, these components are pulled together into a temporary, virtual, computer, providing only what is needed at the moment. 1. This reduces waste and allows for scaling up resources as needed without overloading the system. 2. On-demand processing. Whether you need AI computations, real-time simulations, or complex analytics, the system allocates resources instantly and optimally. Materials and energy efficiency. 1. Photonic components. Much of this architecture is made possible by the same silicon photonics technology used in the I.O.W.N. 1. By using light to process and transmit data, DCI can dramatically reduce energy usage compared to traditional data centers, which rely on electricity. 2. Energy-efficient components. The infrastructure will also make use of next-generation low-power processors, many of which are designed to work with optical systems. 3. Combining wireless with photonics. Extending the reach. While much of I.O.W.N's core infrastructure is based on fiber optic photonic networks, wireless technologies will also play a significant role in extending connectivity to mobile devices, smart cities, and remote areas. Wireless components. 1. 5G and beyond. 6G. I.O.W.N integrates next-gen wireless standards like 5G and 6G for areas where fiber optics are not feasible. 1. These wireless networks will benefit from the low latency and high data throughput of the photonic backbone, making them faster and more reliable than current wireless networks. 2. Free space optics, FSO. A promising technology for wireless communication in I.O.W.N is free space optics. 2. This technology uses laser beams to transmit data through the air over long distances, potentially replacing some radio-based wireless systems. 2. FSO can achieve gigabit speeds without the need for physical cables, though it requires a clear line of sight between transmission points. Solar and energy harvesting. 1. Solar-powered relays. In some remote or energy-sensitive environments, solar panels could be used to power optical or wireless communication relays, reducing the carbon footprint of the network. 2. Energy harvesting. Some devices in the network might also rely on energy harvesting technologies, where they collect small amounts of energy from the environment, e.g., solar, kinetic energy, to power themselves, especially in low-power IoT devices. 4. Reflections of light. Can pure light reflect data without electrical pulses? One of the most fascinating aspects of I.O.W.N is its potential to use light alone to transmit data without the need for electrical pulses in certain parts of the network. This concept is mainly based on passive photonics, where mirrors or prisms reflect and guide light along predetermined paths. In theory, this would allow for near-zero power data transmission over short distances, such as within a data center or between optical devices. How this works. 1. Optical switches and mirrors. In some I.O.W.N use cases, optical switches made from materials like silicon can direct light beams to different pathways without converting them into electrical signals. 1. Mirrors or reflective surfaces can bounce the light between different points, keeping the data in its light form as long as possible. 1. This reduces the need for energy-consuming conversions. 2. Low-power sensors. Sensors and devices that use light to transmit signals could also use very little power by relying on reflected light, making them ideal for low-energy IoT devices. 5. Scalability and flexibility for future applications. I.O.W.N's infrastructure is designed to be highly scalable and flexible, supporting everything from smart cities, autonomous vehicles, to real-time healthcare applications. Its design is built to handle the immense amount of data that will be generated by Internet of Things, IoT, devices, AI, and digital twin systems, virtual replicas of physical systems. Example of future use cases. 1. Digital twin computing. I.O.W.N will enable high-precision simulations of real-world objects and systems, such as monitoring entire cities, predicting natural disasters, or managing energy usage in real time. 2. Smart mobility and healthcare. With the low latency provided by the photonic network, autonomous vehicles will be able to communicate in real time, while healthcare systems can monitor patient data and provide immediate responses through remote surgery and AI-driven health management. 6. Quantum-safe security and sustainability. As quantum computers become more viable, traditional security methods like RSA encryption may no longer be effective. I.O.W.N is exploring quantum-safe encryption techniques to ensure the security of data in transit and at rest. This is crucial given the vast amount of sensitive data that will flow through its networks. Moreover, I.O.W.N aims to meet sustainability goals by minimizing its carbon footprint through energy-efficient components, use of renewable energy sources, and by supporting global carbon neutrality initiatives. Summary of key technologies and components. All-Photonics Network, APN. 1. Transmits data using light, photons, instead of electrical pulses. 2. Achieves near-zero latency and higher energy efficiency. 3. Uses silicon photonics for integration into chips. Data-centric infrastructure, DCI. 1. Disaggregated computing model where resources like CPUs, memory, and storage are pooled and dynamically allocated as needed. 2. Built on photonic components and low-power processors. Wireless integration. 1. 5G and 6G technologies combined with free space optics for wireless data transmission. 2. Solar-powered relays for low-energy environments. Passive photonics. 1. Potential use of mirrors and prisms to reflect light for data transmission without electricity, further reducing power consumption. Quantum-safe security. 1. Preparing for the future with quantum-resistant encryption. By integrating these technologies, I.O.W.N aims to revolutionize global communication and computing by 2030, providing a faster, more scalable, and energy-efficient infrastructure for a smarter, connected world.